Alright guys, let's have a chat about fossils and the fossil record. So, looking at essentially paleontology, which is the study of fossils, it allows us to look at the types of fossils that were preserved at a time, and from that we can determine not only the depositional environment, but also like the climate of that time. So obviously if you've got marine fossils in an area that is no longer marine, it tells you that the climate has changed. So for example, on the second field trip that we go on, we'll be looking at marine fossils that are preserved in a terrestrial area. So we'll be able to determine that at the time that they were deposited, it was in a marine environment. So you can do really cool stuff like that. Fossils are only ever preserved in sedimentary rocks, so you pretty much never see them in metamorphic rocks because of the deformation that occurs. I remember last week when I was talking about how you have things like cleavage forming in regional metamorphic rocks that destroys any fossils, and in contact metamorphic rocks you essentially are cooking the original sediments, so you lose all of those really fine features. So and in igneous rocks you would not see anything preserved in igneous rocks because, like, as you can imagine, probably from all of the stupid films that you've seen, that I know that I've seen, that I absolutely loved, anything that goes into an igneous rock, it's not going to survive. You're not going to have any features preserved. You're definitely just going to end up with more igneous rock. So we only ever find them in sedimentary rocks, okay? And the type of preservation that you have depends on the type of deposition. So if you have something being deposited, for example, in a lake or in the deep ocean where there is little activity, and you just have the finest particles being deposited, you can see really fine features preserved. So in all of the super amazing fossils photos that you've seen, or fossils that you've seen in museums and things like that, where they have really fine, delicate features preserved, it's because that fossil was preserved in something that is really fine-grained. So something that would have been like deposited in a mud at the bottom of the lake or in the deep ocean. So that's where we see fossils being preserved. If you're in a coarser grained material, you're less likely to see such fine-grained features preserved, obviously because the grain size is just too large for it to work properly. So fossils are super important because we use them as time indicators. So we can't give a definitive number on sedimentary rock ages. However, when you look at the fossil record within those sedimentary rocks, you can see, like, you can give like a top and bottom age. So you can say it was between 500 and 440 million years ago. So they're super important for things like that. Whenever you see like plants or trees existing, you know that you are in a terrestrial deposit. If you see things like seashells or fish, you know that you're in a marine environment. And so you can determine a lot about the environment and the climate of the time. So looking into the evolutionary scale, or how evolution has changed throughout geological time, it all starts with microbes. Okay, so little bugs, tiny organisms that live together in colonies. So stromatolites are what we call a living fossil, where we thought they were all extinct because we'd only ever seen them in the fossil record until they were discovered in Western Australia. So in Shark Bay in Western Australia, there are modern stromatolites. So they are what we call a living fossil. And they are essentially bacterial mats that grow in the tidal zone. So And the way that they grow, they build up specific layers. So you can actually go through each of those layers, kind of like tree ring dating. You can go through each of those layers and you can see, depending on how much growth there was, what the type of, like, what the climate was during that depositional period. Okay, and so you can see whether they had a good growth year or a bad growth year, and what that tells us about the atmosphere at the time, and what that tells us about the oceans at the time. So they're actually really, really cool. As far as the evolutionary chain is concerned, we have things where we have explosions of life, where suddenly we go from only a few different types of animals and plants to ridiculous numbers of totally different things that are strange and bizarre and look super weird. We have explosions of life, but we also have mass extinctions. So we have events that have occurred that can almost completely wipe out almost every living thing on Earth. And I'll go through a few examples of how those occur later. At the start of what's called the Cambrian explosion, which is about between 570 and 530 million years ago, there was a huge amount of diversity. And what had happened is that the percentage of oxygen in the atmosphere and in the ocean had changed dramatically, and all of these weird things were starting to come out of the woodwork. And like a lot of them, like the ancestors of those still exist today, which I think is really fascinating. So we say explosion like it's something that occurred fairly rapidly. In geological terms, it was super quick. In normal people speak, it took about 30 million years. So quite a long time. But there was this huge abundance and blossoming of all of these strange plants and animals that were occurring. For example, once we started to colonize, once plants started to colonize the continents, we had grasses and trees and ferns and all sorts of weird things starting to grow. And I mean, if you were a fish that was living in the ocean with lots of big other fish that were trying to eat you, and you just wanted to be your little herbivore self eating grasses and weeds, you'd probably want to get away from all the things that were trying to kill you. So fish started to develop musculature that allowed them to pull themselves through the reeds and onto the grass and out of the water, essentially. So all of the fish that may have been skipping leg day but were super buff, that could actually pull themselves out of the water and drag along the land surface, they were the ones that survived because they weren't being predated. So if you could get out of the water and you could survive breathing air, so they had to obviously not only get super buff, but they also had to have some adaptations occur that allowed them to breathe either in water or on the or breathe oxygen on the land. So weird things like axolotls. I don't know if you've ever had an axolotl. I had an axolotl when I was a kid. Super cool. They live in both water and on land. So they breathe oxygen and can swim, but they're also strong enough to pull themselves out of the water and crawl, essentially. So that was a huge change in the types of creatures that we could see, because we were starting to see things that could breathe oxygen and crawl instead of swim. Obviously, their safety did not exist very long because they started to thrive and become really diverse, and then the predators were like, hey, this sucks, where's all our food source gone? And then you can guess the rest. They followed suit and had lots of ons. So so things just continue to evolve away from the water, starting to crawl. You see lots of weird things developing, particularly in the reptiles. Like the Dimetrodon had this wicked fin on its back, which when you're on land doesn't really serve any purpose whatever, but if you're in the water, it's really good for swimming. And so you see lots of weird things developing throughout the evolutionary scale. Something that you don't see change very much is when we started to develop crocodiles. So during the Triassic is essentially when crocodiles started to evolve, and they haven't really changed much since then. So crocodiles are kind of like the perfect specimen. They're terrifying. I'd never want to be near them, but they're amazing, evolutionary speaking. They're super strong. They're super fast, both in water and on land. And the strength that they have when they bite down on something and hold down on something is ridiculous. Their major flaw or weakness is that they can't open their mouths very well. So, which is why you see scrawny people jumping onto the backs of crocodiles and just holding their mouths closed with their hands, because they don't have that strength of their jaw to open it whenever there's pressure on the outside. So that's probably pretty much their only evolutionary weakness, is that they don't have strength to open their jaw. But boy howdy do they have it when they close their jaw. So crocodiles are essentially modern dinosaurs, which we probably all knew already. They're super cool, and I kind of want to be a crocodile when I grow up. But there were all sorts of different dinosaurs, from things like, I'm sure you're all familiar with the T-Rexes that you see in Jurassic Park, as well as the types of birds that were developing at that time. So sorry about that. So dinosaurs started to evolve to develop from just cold-blooded to warm-blooded. So we started to see creatures that have a really high metabolism and really high metabolic rates, and so we started to develop birds, which are really cool, and like chickens, also terrifying. Oh, geese, oh my goodness, just as scary as a T-Rex. I don't know, just ignore that. Let's pretend I didn't say that. Anyway, but during the Mesozoic is when we started to have these really, really big dinosaurs occurring. So like sauropods, for example. So like Littlefoot, if you haven't seen The Land Before Time. If you haven't, definitely recommend watching it. Totally scientifically accurate and super cool. And will break your heart. Oh my god. Okay. So, during the Mesozoic, obviously, if we're starting to develop warm-blooded creatures, we're starting to develop mammals, okay? So, things that, even after birth, were relatively helpless, and so they required parental care. So, milks, and they had placenta, and all sorts of things that we now know are common with mammals, started to exist during the Mesozoic. So the types of fossils that you have and the types of preservation that you have, you can have a whole host of different types of ways that fossils can be preserved. Like the fantastical preserved in amber, like you see in Jurassic Park, as well as lots of things like trace fossils, like burrows and footprints. If you have things like that are called casts and molds, okay, where, say, I have broken my arm, which you would be able to tell if you were to look at the bones preserved of my arm, that there were breaks in there. If I have what we call a cast on the outside of it, that's actually technically a mold. So it's taken a mold of the outside of my arm and preserved the shape of my arm. Okay, so we call that a mold. So if I was to remove my arm from that mold and then infill it with something else, something totally different, then that is what is called a cast. Okay, so the mold is the actual material covering the outside of my arm, and then the cast is actually the replacement of my physical arm with something else. And so you can have all sorts of things doing that. So for example, when we talk about hydrothermal fluids, you can have quartz being deposited in this empty space within the mold, and preserve like a physical perfect replica of my hand. It could even potentially preserve down to fingerprints if the material that the mold was made out of was fine-grained enough. So if you were in like a really fine-grained mud or something like that. You also have weird things like carbonation when things are fossilized. So next week when we go on our first field trip, we'll be looking at some fossilized trees. So they're petrified, okay, where essentially all of the cavities and pores within those trees were replaced with something, with a specific type of mineral. Yeah. So there's heaps of different ways that things can be fossilized or preserved. Coprolites are probably one of the funniest types of fossils, which is essentially just, it's poop. It's fossilized poop, or stomach contents, as most people like to call it. That's just been preserved wherever it was deposited, and that's, yeah, it makes me really laugh that fossilized poop is so common that it's got its own name. Anyway, on the other end of like life explosions, we have mass extinctions. Okay, so there's heaps of different reasons that we can have a mass extinction occurring. It can be climatic, it can be from competition, it can be excessive predation. For example, human beings have made heaps of things extinct lately. And so whenever you have these major environmental changes occurring, you're going to start seeing a lot of creatures going extinct. So there's been a lot of mass extinctions throughout time, like the late Ordovician, the late Devonian, where almost 88% of animals and creatures came extinct in both of those. The Permian-Triassic boundary, which is the most severe, which was almost up to 97% of species became extinct. And then the Triassic-Jurassic, Cretaceous-Paleogene, and then the current one, which is the Anthropocene, which is the one that we're responsible for. So some of those extinctions that have occurred from planetary impacts, meteorite impacts, volcanic eruptions, like human impacts or excessive hunting, sea level change. Obviously, if you're an animal that lives in the swampy marshlands close to the ocean, if there's a sea level rise, you're going to have a change in not only the chemistry of the water that's there, but also the plants and other animals that are going to be living there as well. So everything kind of has to shift backwards and move around. The Siberian traps that I mentioned earlier, did I mention those earlier? Which was, hang on a second, the Permian-Triassic boundary was the traps, where we had this massive outflowing of basalt. And so obviously if you think about basalt flows like what we see in Hawaii or in the Hawaiian island chain, there's a lot of hot liquid rock that's flowing, but that's not all that extrudes when basalt erupts. Okay, so you have lots of those different gases pouring out as the like as this hot molten material comes up from the crust and extrudes out onto the surface. And if you have a constant eruption, or like a constant large-scale basaltic eruption occurring, you're going to start messing with the atmosphere, and you're going to start messing with the chemistry of the oceans, what types of plants and animals can exist because you're messing with the atmosphere. And so you just see these massive extinctions of animals and plants that just can no longer exist in that environment because it has become toxic to them. So yeah, so there's a number. Sorry, my laptop's going low, so I'll have to wrap this up. So there's a number of different mass extinction mechanisms. Okay, meteorite impact is another one that is common and huge. So essentially, the initial impact collides with the Earth and blasts a whole amount of debris up into the atmosphere. When we have all of that debris in the atmosphere, we start to have global cooling occur. Okay, so if you've got heaps of dust and debris in the atmosphere, the sun beams that are coming down are going to hit that debris and then bounce back out. Okay, so we aren't having any of the absorption that occurs on the Earth's surface because everything's getting deflected back up in the atmosphere. So the more material you have in the atmosphere, the longer it will stay up there, the longer that we're not having those solar rays coming in and warming the Earth's surface, so we have massive global cooling. Okay, and so that type of thing is really catastrophic, and even like the impact was instantaneous, but the after effects felt for like hundreds or thousands of years after that, depending on the amount of debris that there was. So yeah, it's huge. So for example, the KT boundary is that suspected meteorite impact that we were talking about the other day. And so on slide 44, we're specifically talking about the Chicxulub crater. And by looking at the gravity anomaly, that's the one that's starting to get destroyed by subduction. And yeah, so I think the rest of the lecture is essentially just giving specific examples of the KT boundary and then the PT boundary, mass extinctions. And so have a look through the slides, and yeah, and I'll do another video either later tonight or tomorrow on the intro to plate tectonics. And I hope you've enjoyed this and that I haven't raved on too much. Let me know. I'll see you tomorrow.